Hi everyone, this is Santosh from Stevens, and today I'll be presenting our work Seesaw, a framework for graph sampling and random walk on GPUs. Starting with graphs, graph provides a natural representation for most data and are widely used. They are mostly used to represent social network like in Facebook and Twitter. They are used for web networks for specifying connection of web pages. They are also used in knowledge graph for representing relationship among different entities. A plethora of algorithms exist for mining crucial information from graphs. Generating embeddings, visualization of graph data, and graph neural networks are some of the example algorithms. Plenty of graph processing algorithms are available which are not listed here. But real world graphs are large, ranging from millions or billions of vertices and edges, and applying these algorithms directly over large graph incurs huge storage requirement and computational cost. Hence, extracting information from a large graph is challenging. Graph sampling and random walk algorithms are used to overcome the challenge of processing these large graphs. Instead of directly applying algorithms over a large graph G, we can randomly sample or randomly generate a batch of graph samples or random walks. As samples or random walks are reduced representation of graph, the memory and computational requirement for processing them is also very low. Instead of using whole graph, these instances of samples or random walks can be used as input for the algorithms. Without this technique, the cost of processing large graph could be really exponential. Furthermore, using samples or random walks help us to make the algorithms more scalable. We can use these samples to allow an application to train and perform prediction or compute embeddings from large graph. For example, using sample reduces the cost for training graph convolutional neural network, and another application Node2Vec also uses random walk to generate graph embeddings. As we have established the importance of random walk and sampling algorithms, let's take a deeper look on how we generate samples or random walks for a graph. So for generating samples in random walk, we start from a randomly selected source vertex. Here we have vertex 8 and randomly traverse immediate neighbors for each vertex up to certain steps. Here vertex 5, 7, 9, 10 and 11 are the immediate neighbors of vertex 8. So first we define the transition probability for each neighbor vertex. For defining transition probability, can be defined as degree of vertex upon sum of degree of all neighbor vertices. We can call this transition as bias edge transition, as transition to neighbors depend upon a bias or transition probability, and every neighbor have different transition probability. Here for vertex 8, the sum of degree of all neighbor vertices is 15. For example, as the degree of vertex 7 is 6, each transition probability is 6 upon 15. Similarly, we can define the transition probability for other remaining vertices. For random transition, we need to generate a random number between 0 and 1. For generating random number, we denote it by a dice roll, and the generated random number is always between 0 and 1. After we have the random number generated, based upon that number, we select our immediate neighbor of vertex 8. Here we select vertex 7 for our next source is our next source vertex, and we repeat the process from vertex 7 for certain step to generate complete sample or random walks. Now we have a background on how sampling or random walk is performed, but there are a lot of variation of these algorithms. If we have a framework, it will allow us to implement sampling and random walk algorithms with just a few lines of code without any headache. Frameworks can be very handy if we want to implement different algorithms. Let's have an overview on available framework for sampling and random walk algorithms. Two related works propose a framework. The first one is GraphSim, which focus on defining sampler for generating graph embeddings. The second one is NightKing, which is a distributed framework for random walk algorithms. Moving towards the limitation, both GraphSim and NightKing lack support for majority of traversal-based graph sampling algorithm and also do not support GPUs. Here, we exclude simple random node or random edge sampling. This brings us towards our first challenge, which is building a generic framework which can support all or different variation of algorithms. Our proposed framework Seesaw is the first framework in our knowledge able to support both sampling and random walk algorithm with GPU support. Let's see how Seesaw framework can be used to implement these algorithms with multidimensional random walk as an example. This random walk starts with a randomly generated frontier set or a frontier pool. Here we have vertex 8, 0 and 3 in the frontier pool. First, we sample a frontier vertex with vertex degree as a bias, and here the sample frontier is vertex 8. Next, we need to gather the neighbors of vertex 8 and sample one of the neighbor with equal probability or unbiased selection. The sample neighbor is 7, which is also added to the sample edge list. Next, we update the frontier with sample neighbor by replacing vertex 8 in the frontier pool with vertex 7. One thing to note is that almost all sampling and random walk algorithms can be defined with similar flow, but they differ in two important things. First is how the bias is defined. As we can see, the sampling could be biased or it could be unbiased. And the second important thing is a method to update the frontier set. Now let's see how Seesaw can implement these algorithms. Our first API, which is vertex bias, define how a frontier is sampled from frontier pool. Second API is bias, defines how a neighbor is sampled from neighbor pool. And our third API update defines how a frontier is updated based upon the sample neighbor. As we just saw how Seesaw can be used to implement an algorithm, let's look at the overview of Seesaw framework. Seesaw provides three simple and expressive APIs, or we can call them user programming interface, which can support existing algorithms and also have flexibility to support emerging algorithms, as most sampling and random walks algorithm are different in terms of bias and how they update the frontier pool with the sample neighbors. The main function uses these APIs for implementation and is optimized for GPU. The users do not need to know about the complex implementation of Seesaw to define sampling and random walk algorithms. With this, we address our first challenge for a generic framework. After introduction of Seesaw framework, let's see how we can optimize Seesaw for some sampling algorithms. While most random walk algorithms sample only a single neighbor, but some graph sampling algorithms like layer sampling or neighbor sampling need to sample more than one neighbor from a vertex with a bias. Here, taking the figure as an example, we have vertex 8 is the source vertex and we need to sample two neighbors of vertex 8. For faster sampling, we use two different threads to sample each neighbor. As each thread samples independently and concurrently, the sampling should be faster. But with bias sampling, different threads could sample the same neighbor. Here, both threads try to sample vertex 7, which is not allowed if we do not want any duplicates. We term this duplication as selection collision, which is another challenge. And this challenge is not efficiently addressed by any of the previous work. One solution for selection collision could be updated sampling. In this method, we update the transition probability after sampling each neighbor. Here, we first sample the neighbor 7 randomly, then vertex 7 is removed from the neighbor list and the transition probability is updated for the remaining neighbors. We perform sampling again with updated transition probability, and this time we sample neighbor 11. As the sampled vertices are removed, we avoid selection collision from happening. But updating the transition probability after each sample is very costly. Another solution for selection collision is repeated sampling. In this technique, we repeat the sampling until we acquire unique neighbors. First, each thread samples neighbor independently. As there is a selection collision for a thread in vertex 7, one thread repeats the sampling process. There is again a selection collision as vertex 7 is sampled again. Finally, in another repetition, the thread is able to sample a unique neighbor. This method also solves the problem of selection collision but may require higher number of repetition. We propose an efficient solution inspired from both updated sampling and repeated sampling, which we term as bipartite region search or BRS. If selection collisions occur during sampling, we update the random number in such a way that we jump from vertex 7. The update corresponds to a virtual removal of vertex 7 from the neighbor list. Then we repeat sampling with updated random number in a new region. With this technique, we reduce the number of repetition for sampling and avoid costly update. With BRS, Seesaw solves challenge 2 more efficiently. More details on how BRS works can be found on the paper. As discussed earlier, real-world graphs are very large. The average amount of memory in recent GPUs is 16 GB, with a model of V100 GPU having up to 32 GB memory. The size of the graph in CSR format for graphs like Friendster and Twitter is 29 GB and 22 GB, which is larger than the average memory size of recent GPUs. Even with GPU memory size of 32 GB, graphs like ClueWeb 12 and UK 2014 have higher than 100 GB space requirement. This brings us to a third challenge: handling large graphs which are larger than memory size of GPU. For sampling and random walk, we observe that entire graph is not required to be stored in the GPU memory. We only need the active frontier and their immediate neighbors for each step of sampling. This motivates our solution out of memory sampling with 1D partition. Let's see an example of out of memory sampling with Seesaw. Assume we are sampling randomly generated source vertices 0, 2, and 8. We partition the graph by equally assigning the vertices to different partition P1, P2, and P3. Here, each color represents a partition in the figure. At first, we have frontier in the CPU side. Then, we determine the active frontier vertices for each partition. Here, P1, P2, and P3 have 2, 0, and 1 active vertices respectively. Our first optimization, workload-aware scheduling, determines which partition to sample based upon the workload. The partition with higher workload is scheduled earlier, as it helps to reduce the overall partition transfer to GPU. Assuming we can only sample 2 partitions, we select P1 and P3 for sampling. Our next optimization, workload balancing, allocates computation resources based upon the workload. As the ratio of workload is 2:1 for P1 and P3, the computational resources is also allocated in the ratio of 2:1. Then the partitions are transferred to the GPU side for sampling. Each partition have its own frontier queue in the GPU memory. After first round of sampling, P1 have one frontier, P2 have two frontiers, and P3 have zero frontiers. Each selected partition at an iteration continues sampling as long as they have some frontiers. As P3 do not have any active frontier, sampling terminates for P3. In the next round, only P1 is sampled, which results in addition of one frontier vertex in P2, and sampling terminates for P1. As sampling for both P1 and P3 have terminated, one iteration is completed with 3 vertices in frontier queue of P2. For determining next partitions and resource allocation, the queue size for each partition is passed to the CPU side. We repeat this process until the frontier is empty. With this out of memory sampling, we address challenge 3. Moving on to the evaluations, we perform all tests on Summit Supercomputer from Oak Ridge National Lab. Each node is equipped with 6 V100 GPUs with 16 GB memory and dual socket 22 core Power 9 CPUs. We use 10 different datasets for evaluation. More details on graph datasets and size can be found in the paper. For comparing our work with related works, we use sample ages per second or SAPS in short as a matrix. It is computed as total number of sample ages upon total time for sampling. For comparing with state-of-the-art methods, we compare our results with NightKing and GraphSynth. For NightKing, we use biased random walk, and for GraphSynth, we use multi-dimensional random walk. The length of the random walk is kept 2000 and number of sampling instances or random walks is 4000 for all comparisons. The graph shows million sample ages per second achieved for different datasets. Compared with NightKing, we achieve 10 times and 14.7 times speed up with 1 GPU and 6 GPUs. And we achieve 8.1 times and 11.5 times speed up with 1 GPU and 6 GPU respectively for GraphSynth. For multidimensional random walk, we use a frontier size of 2000. Next, we compare the scalability of Seesaw with multiple GPUs using neighbor sampling algorithm with 8000 instances of samples. The graph shows the speed up achieved with different graph datasets. We achieve up to 5.2 times speed up at max with 6 GPUs. More detailed evaluation of Seesaw along with profiling of each optimization can be found in the paper. In conclusion, Seesaw is first generic GPU-based framework for both graph sampling and random walk. Seesaw outperforms both state-of-the-art implementation by 14.7 times and 11.5 times for NightKing and GraphSynth respectively. Seesaw also provides efficient out-of-memory sampling for handling larger graphs. For future improvements, we will be adding support for more sampling algorithms and improving the existing sampling techniques. The source code of Seesaw is open source in GitHub. Please check out our paper if you find this work interesting. Thank you.